Good morning, everyone. In the last class, we started our discussion about classification problem. So maybe I will quickly summarize that. Let's try to have a relook at that and restate that problem again. Let us consider that omega, let's say the classes that we consider be there are m classes, okay, into which we want to classify a given um, sample characterized by a given its feature vector. Let the classes be omega 1, omega 2, and so on, omega m. Okay. And what else? Let x bar be the L dimensional feature vector characterizing your sample. So this is x1, x2, so on, xl, your L dimensional feature vector. Now, how did we define the problem now? Classification problem is equivalent to what? Given this information. In terms of statistics and probabilities, we have formulated that. So what is the problem that needs to be solved?
Sir, problem of this vector lying in a particular class given the features of the vectors.
Right. So can you just
Probability.
say it in the mathematical terms of the probability of what is that we want to solve here?
Probability of omega I given x bar.
Probability of omega I given x bar. Very good.
And
So you now you what is it that you are going to do? You are going to compute it for all, yeah, for each individual class and among them. So you are given an x bar value. Now you see that but with what probability it can belong to class 1, class 2, class 3 up to class m. And then which one do you choose? Choose
maximum.
a class J for which the probability of omega j given x bar is greater than probability of omega I given x bar, where this for all values of I that is not equal to j. So for any other class, when you compare it, this should have the maximum value, right? Then you will assign this x bar to that jth class. So this is how we defined the problem in the last class, is that you need to essentially compute for each class I probability of omega I given x bar, and you need to pick that class which has this probability maximum. Now, the follow-up question is what we will pursue now in this class. How can I find out probability of omega I given x bar? All I know here is x bar. I know which are all classes are there. So I'm given now an x bar. How can I know what is the probability of this belonging to a class, ith class, for example? Well, from here, there is no way you could see that. And what comes to our rescue here is Bayes' theorem. So how this theorem will help us, you would, if you are with me, if you also work out with me till the end of this class, if you can manage to work along with me, you would be able to realize and appreciate how we would be able to compute these values. So for a moment, just hold on with this term, but let me introduce you the Bayes theorem. I'm sure you would have come across this either in communications or in probability course or somewhere else. So let me first write this Bayes theorem and then we will go ahead. Suppose I'll write the first term here, probability of omega I given x bar. Can any of you help me with writing this now? That is the first term I want to write, multiplied with the probability of something is equal to something else. So can you help me with that? What the Bayes theorem tells us? Also see,
Probability of x bar
very good. Yeah,
first
happy to
one
hear such
equal to
response.
probability of omega I union x
Probability of
bar.
Intersection x.
Sir, here it will be probability of x bar given omega I
That's right. Into probability of,
into omega.
very good. So when you have a conditional probability there, probability of omega I given x bar multiplied with whatever has been given is what, with what you are multiplying there, will be exactly equivalent to probability of x bar given omega multiplied with probability of omega. It is given omega, that given omega is what it is, with that probability you multiply it here. In the interest of time and in the interest of what we want to cover, I will not go into the details of proof of this theorem. Nevertheless, every signal processing, every person who is working in this area should know it. So I leave that part to you, okay? Because that's very fundamental and should have come across earlier itself. Right. Now, what is it that we need to find out? This part is what we need to find out. So how can I write that? Probability of omega I given x bar is equal to probability of x bar given omega into probability of omega. Okay, or since I am writing I here, I should have written I here also, isn't it? So x bar given omega I into probability of omega I divided by probability of x bar. No, doesn't it look more complicated? Initially I had to simply find out this. Now I have used Bayes theorem and made it, I introduced now three probabilities here. Well, there is a way you could calculate these three terms. On the other hand, there is no way you could right away compute. What is this referred to as? Earlier in the last class, we had there is a naming ceremony happened for that term in the last class. Two names have been given. One alias has also been given to it. What were the names to that?
The conditional probability and posterior probability.
Conditional probability,
And posterior probability.
a posteriori probability. Not posterior, you call it as a posteriori probability. Okay. Conditional because given x bar, that's the condition there. A posteriori because the classes are already existing. Now you have the x bar, and from that you need to make a assessment there. Now let's start. Now I want to compute this. You are given this. Okay, so let us see now how each of those terms can be computed given a training data set, or having some prior knowledge about that. Okay, so let's start with a simple one. Let us also make one assumption such that the writing of equations would become easier for us. Let's assume that m is equal to 2 here. That means I'm assuming that there are two classes here. So omega 1 and omega 2. Okay. Now, with that, let us go through one by one these three terms here and try to make a sense out of that. Okay, listen carefully and follow me carefully. Otherwise, as I said, you may even on an extreme, you may think that I'm even bluffing you guys with just changing omega I given x bar to x bar given omega and many other things. Okay, it looks like just like a gymnastics of few terms. Okay, so let us first go through probability of x bar. It is, what is this P of x bar? Is nothing but probability density function of x bar. That's what this is. So if you give me an x bar value, I should be able to give you a number associated with that, with what probability that x bar could occur. Now, let me pose the question in this manner. I give you now, anyway, I considered m equal to 2. So there are these things, probability of x bar given omega 1, probability of omega 1, probability of x bar given it belongs to omega 2. What is the probability that that belongs to omega 2? Right. So now can you express probability of x bar in terms of those four probabilities? Why you want to do that? Because you would later realize that you could in fact compute them from a given training data set or in different other ways. Another point here, make a note. See, X bar should either be in the class 1 or class 2. There is no other way. It cannot go anywhere else. Now you answer my question.
Sir, it will be probability of x bar given W1 omega 1 into probability of omega
Probability
1
of X
plus
bar given
given
omega 1
omega 1 into probability of omega 1 plus probability of x bar given omega 2 into probability of omega 2.
X bar given omega 2 into probability of
Probability of omega 2.
Very good. Very good. That's right. So it could be, suppose you are told that it belongs to class, listen to me, pay your full attention here. Suppose if I tell you that it belongs to a class omega 1 with a probability of omega this one. So now it is given, all you need to do is, what is the probability that given it belongs to omega 1, what is the probability of X bar here? Given that it belongs to omega 1, in that class, what is the probability of having this feature vector? Similarly here, if it is PW1, here the probability of omega 2 here. And of course, if it is just two classes, can you write the probability of omega 2 in terms of probability of omega 1 also?
So 1 minus probability of omega 1.
That's all. There are only two possibilities are there. The summation should be 1, and that eventually would result in this having a PDF there. Now, if you want me to write it in general for any number of classes, okay, then I could put the summation here, easy to write. I varying from 1 to m. Now you help me in writing the expression inside. So
So
inside the
probability of x
summation,
bar
probability of X bar
given omega I
given omega I
into probability of omega I.
into probability of omega. Very good. This is my probability P of X bar, which is nothing but probability density function of X bar. Now, let's go to the next easier term. Probability of omega I. We'll go to probability of omega I. We considered two classes here. So we can write it as probability of omega 1, probability of omega 2. These are the two probabilities that are there. What do you think these are called as? So it's the probability of occurrence of a class 1 sample, and another is probabilities of occurrence of a class 2 sample. So what do you think these are called as? Prior probabilities that you know in the class, for each class, the prior probabilities for each class. You may typically know it. Assume you are doing, for example, typically assume, let me begin with some maybe a medical imaging problem where in the brain scan, you have cerebrospinal fluid, gray matter, white matter. These are the three things that are there. Then you know roughly what would be typically the proportions of gray matter, white matter, and cerebrospinal fluid. From that prior knowledge, you could say what are the probabilities of classes omega 1, omega 2, and omega 3. Okay, that's one real example I have given you. Now I will give you, now let us move to a generic example where I have only given you a training data. Now you tell me, is it possible that if I give you a training data where you know to which class each of those feature vectors, so what do you mean by giving you training data? What do you think does it mean in terms of the variables or parameters that we have defined so far, what do you think it means when we say I have given you training data? What do you think I have exactly given you?
So set of feature vectors and associated class.
Very good, very good. All you take is, let's say, x1 bar, x2 bar, so on. If you're, let's say you have n samples in your training data set, xn bar. This is a feature vector, L dimensional feature vector. So X, each one has L components. Along with that, I have given you, that means if I gave you training data set, means whether that will that belong to omega 1 or omega 2. Each of them I have given you. Let's say this belongs to omega 1, this belongs to omega 1 again somewhere. So I have given you this information. This is my feature vector. For this feature vector, it is belonging to so and so class. This is what I have given you when I say I have given you the training data. Now, assume that I have given you this training data. Can you tell me how you can compute probability of omega 1 and omega 2, assuming that your training data is not biased towards any specific class? By that statement, what I mean is the proportion of classes that I would expect in the training data versus the real-time data is same. Okay, that is the assumption when I say this is not, see, when I say the training data is not biased, it doesn't mean that I have equal number of samples for each class. That's one way. In a different perspective, in a different context, you may do it. But for now, when I say it is not biased, what I mean is the proportion of samples that I could expect for each class are in a way they reflect what I could expect in while I am testing it. Is that statement clear? So hoping that that statement is clear. Now you tell me, if I give you this training data, how are you going to compute the prior probabilities? These are all the problems you are going to do it. So you should be able to, these concepts should be very clear to you. How do you compute that now? Any thoughts about that?
So it's number of feature vector belonging to a particular class divided by total number of feature vectors.
Is all very good. Very good. That is all you need to do. Assume that there were n1 samples or n1 feature vectors. Okay. That here out of this capital N that belongs to class omega 1. And similarly, there are n2 samples that belong to class omega 2. And of course, here there are only two classes. So n1 plus n2 should be equal to n. Now, can you give me the expression for probability of omega 1 is equal to? Probability of
So
omega 1
N1
is equal.
upon,
That's all. N1 over n. And probability of omega 2 is equal to n2 over n. That's all. This is how, from a training data itself, you can compute prior probabilities. Let's again come back to this apparently complicated equation. This one. Well, we figured out I could compute probability of x bar from these. If I know these two terms, I can compute it. So it boiled down to computation of two things. Now I am done with this thing also. So I am done with the PDF of x bar. I am done with the probability, prior probabilities of each class, probability of omega I. All I am left with now is probability of x bar given omega I. This is all I need to know. If I could crack this term, how to computation of this term, I am done with this whole stuff. So what we are saying here is, I'm already telling you that you have given me an x bar. I'm also telling you here, anyway, I can take 1 and 2. So it can either belong to omega 1 and omega 2. So what is this probability telling you? What this probability should convey is that, suppose given that it belongs to a class omega 1, what is the probability of having this x bar feature vector, right? That's what it is telling you. And so this is also referred to as likelihood function. How likely is that this has this value? So this is also referred to as the likelihood function. And to be more precise, likelihood function of omega I with respect to x bar. This is how likely is that this belongs to that. Or maybe to make it more clear, just let me put it this way. Let us keep, to make the drawing simple and understanding easier, let us take L equal to 1. What is L in our definition? L is the dimensionality of your feature vector x bar. So my feature vector has only just one value, easy to draw. Okay, so this is my x bar. Now it is just a scalar here. Now probability of x bar given omega is what I'm going to plot on y-axis. For example, assuming some distribution of whatever the distribution is, it will tell me now what is the probability that this, given that this belongs to x omega I, what is the probability of that happening? Okay, so if I could somehow get the distribution for each class, if I could get the distribution for each class, this could be, for example, anyway, I have just two classes. This would be probability of x bar given omega 1, let's say. This is probability of x bar given omega 2. Then what is it that, how do we compute this? If we know the distribution and given an x value, now x is what you would get from the new sample. And let's say I have it somewhere here, given that it belongs to, let's say, omega 1, you will see that, well, that probability is pretty low. It's outside your Gaussian, it's very far from your Gaussian distribution. And similar interpretation for given an x bar, probability of x bar given W2, given that it belongs to W2. Just keep in mind two things. There could be noise because of that. Sometimes the distribution that having a very far away also, it might still belong there. So, and that is one thing. And we have discussed another point also. There is not a unique point here. It's a statistical distribution of each class that is there essentially. So that is what we are going to make a, or this term is going to give you this likelihood function of omega I with respect to x bar. Is that clear? Or this term of likelihood function of omega I with respect to x bar, I'm calling it is with respect to x bar because you are given an x bar now. You know, now you are also given that, let's say it belongs to omega 1 or it belongs to omega 2. Then this is the one which gives you the likelihood values. I give you again the earlier training data. Is it possible to compute these distributions from that? I give you the earlier training data. And maybe I give you some assumption also to initially simplify things. Later, as we move on in this course, we will relax those assumptions also. But for now, I will give you an assumption also that each class has a Gaussian distribution with respect to the feature vector. Okay, so let us simplify things. There is only we are calling it feature vector for time being. Let's consider its dimensionality is 1. There is only one feature vector, has only one element there. Okay. So now let us make an assumption that each class has a Gaussian distribution with respect to your feature vector. Now, after that, I give you probability. I will ask you about what is the probability of X given omega 1. I ask you to compute probability of X given omega 2. Will you be able to give me these values? Or even question before that, will you be able to give me this plot now? I have given you a sufficiently large training samples. You already know what it means now when I say I give you a training data. Now, can you give me I also have given you the hypothesis or maybe the statement that each of this class has a Gaussian distribution with respect to X. Now, can you give me these distributions if I tell you this? Can you compute these distributions from the training data? Is it possible?
Yes, sir.
How do you compute?
So by calculating mu and sigma from the training data set for each class.
That's right. That's right. How do you compute that? Just give me, your answer is absolutely right. Just tell me a little more detail. I have given you, you know what exactly I have given you, right? This is the table I have given you. I have given you on one column, I have the X bar value, here just an X value and omega value. How do you compute it? Your answer is correct, but I want a little more detailed response there.
So mu for omega 1 can be calculated by summation of all xi vectors belonging to omega 1 divided by n1. And similarly for omega 2, summation of all xi vectors belonging to omega 2 divided by n2.
That's all. You pick all those samples that belong to omega 1. You compute the mean value of it. You know, the mean is summation divided by the total number, and then 1 by n into, you do x minus mu whole square. Okay. Let's say there is I values, there are 1 to n. So each sample xi minus n, you do that, you get the variance. Once you know the mean and variance, you will be able to draw this. So then you do it for all, you pick all those in the training samples that belongs to class omega 1, then you do this calculation, you get to mu for that particular class. So let's say mu 1, maybe for class I keep it on the top here, mu 1. Similarly, you do for the another omega 2, you take the mu 2 there. Okay, that's all you do. And for within that class, you see how within those samples how much variance is there. Okay. Now again, let's come back to the basic first equation here. Now you know probability of X bar given omega I. You know the probability of omega I. If you know both, you know this. If you know all these three, you could compute this. And here, by varying omega I, this would vary. First time you do this probability of X bar given omega 1, probability of omega 1 here. And then you vary I equal to 2. These terms will be different. You compute that. And then what did we say in the very beginning? You pick that, choose that class which has the maximum one. That's all. That will tell you to which class this new sample belongs to. Hope everybody is able to connect all these steps and see how you eventually compute there, and hope you are not misunderstanding me to just use some jumbling of words or terms here. Hope this is clear, and hope every one of you is clear on how the Bayes theorem is helping you to figure out these conditional probabilities or a posteriori probabilities. I'll clarify a couple of things here. First thing, in the ground truth, when we say training data, you know to which class it belongs to. And in order to compute mean and variance, one sample is not enough. Our very assumption here, of course, Gaussian is the very first assumption. Then further assumption is that, and which is not an assumption, which is required or a prerequisite or a requirement, is that you have sufficiently large number of samples such that you should be able to learn from it a distribution that in fact would represent what you could expect in reality. If I have very few samples, how good is your class? Suppose I would like to know. If I interact with only one student or two students, it will not be good enough. Assume I have a class of 100 people. Now, the first thing is I should at least should have 20 people I should have interacted with. Second thing is, whatever this subpopulation of 20 that I have picked out of 100 should represent in a in an unbiased way what could be the distribution that I could expect out of 100. This is the second thing. Third point I want to, so these are the two things that should be there. And this you could see here, there could be always an overlap between two Gaussian distributions. It only tells you that it is not necessarily due to noise, because in practice you may not be able to separate them all the time, the distributions. Rightly so, they may have some overlap. It could be, you have seen many images and then segmentations of that. You could have some intensities inside the same, the same intensities might be present outside that object also. So, well, there could be a noise, and statistical variations within that population also could be there, or the class could be there, which is giving you this distribution, but never attribute it to solely to the noise. That's the another. All you could say is the probability is less. That means assume that these are the intensities. If you have 100 pixels with a given intensity of this, out of that, suppose if I have all it will tell you is, let's say with a 10% of those pixels belong to class 2 and 90% of the pixels belong to class 1. It is not noise. It is, assume even without noise, this can happen. But when you have to probabilistically deal with it, it may so happen that you are okay with committing this 10% error and you might give it to the class 1. But in the training data, you would realize that there are indeed 10 out of 100 samples for which they might be having this particular intensity, but still belong to omega 2. Are these 2 points clear?
Yes, sir. So that will be the reason for error, as in what we had
Correct.
discussed
Exactly.
in the first.
Exactly. So there are instances where you do have some uncertainty. Then you go by probability. That's all you could do there.
Understood.
Sir,
Yes. Yes, please tell
that
me.
there can be common feature that is shared by omega 1 and class 1 and class 2 is that if it is shared, then n1 plus n2 is equal to n will not be possible. No, sir. Common.
What you mean is, it's not common feature. Can a given feature vector or a sample, can it belong to both classes? That's your question, right?
Yes, sir. Yes.
Right. So then this doesn't work. Right now, we are not doing a fuzzy classification. They call it as a fuzzy classification, where you will not take a call on that to it can belong to both classes. That is not the case that we are considering here. Then things are that requires a modification through various steps that we are doing here. You are right. Then what needs to be done is you need to compute this PW and probability of omega 1 and probability of omega 2 in a different way. This doesn't work out. This is just, I have taken a case. This is also the case that we would discuss for the most of our course, where a given sample can belong to one of the classes, not to multiple classes. That is how we are calculating these prior probabilities. But if that is not the case, with some other prior information, then you need to compute this PW of 1 and probability of omega 2. Is that fine?
Yes, sir.
Good. Let me take one more step from here on how you compute these things. So basically we told there So let's like bring it to some conclusion here on how you compute them. Let's write it in a more concrete way. What we have mentioned is, we just considered two classes, omega 1 and omega 2. And what did we say? If your probability of, first of all, it is the posterior probabilities that we need to compute. So omega 1 given x bar, the x bar is given to you when you take it. If it is more than probability of, okay, I'm not writing PR, so let's just write to P itself here. Let's follow consistently the same notation. If it is probability of omega 2 given x bar, then what you do, assign to, or maybe let us write it x, then you would say x bar belongs to which class? X bar belongs to, hope I did not ask any complicated question. If that is the case, x bar belongs to,
Omega 1.
that's all. X bar belongs to omega 1, and else x bar belongs to omega 2. Now what we did is, well, there is no way I could right away know these values. I profited from Bayes' theorem, which is telling me that this term would be in fact equivalent to probability of x bar given omega 1 multiplied with the probability of
omega 1
omega 1
divided by probability of x bar.
divided by probability of x bar. So how could I write now? If this is greater than probability of x bar given
Omega 2
in multiplied with probability of omega 2 divided by probability of x bar, then what you do? Then you would say x bar belongs to omega 1, and else I would say x bar would belong to omega 2, isn't it? Now, anyway, probability of x bar is common in both, so I would just drop them out. This is a multiplication factor that just scales both in the same with the same value. So all I could say now is, if probability of x bar given omega 1 multiplied with the probability of omega 1 is greater than probability of x bar given omega 2 multiplied with probability of omega 2, then I would say x bar belongs to omega 1, else I would say x bar belongs to omega 2. Okay, now there could be quite a few instances where you do not really know prior probabilities of omega 1 and omega 2. If you know it, you will include it. Okay, if you don't, if you're the way you get them, if it's not reliable or exact representation of your full sample, then maybe you would assume they both of them to be equal. That's also is there. So for the time being, we will later again bring this prior probability guy into the picture, but just for now, to get some inferences, let's assume for now, assume that your probability of omega 1 equal to probability of omega 2 equal to what then, if they are equal? Anyway, there are only two classes. If they are equal, what should be those probabilities?
1/5.
1/2. So that means if I assume this, what is it this turns out to be now? If, what is the condition I need to look at now? If probability of x bar given omega 1 is greater than probability of x bar given omega 2 then you would say X bar belongs to omega 1, else you would say X bar belongs to omega 2, with the assumption that these two probabilities are equal. So if you notice, we made a transition from a posterior probabilities to likelihoods on the assumption that prior probabilities are same for all the classes. That's what we did here. So again, let's just assume that we computed this. There are different ways to compute this. I just tell you one Gaussian one, but we will deal with them in more details later. But just assume that these are the two graphs or distributions that I got for the probabilities of X bar given omega 1, and this is for probability of X bar given omega 2, and of course it's an L equal to 1 here for X bar. So if you want, I could write X here, and of course my y-axis is probability of X bar given omega. Now, can you tell me for which values of X I would be assigned by this process? I would be assigning a given feature vector to class 1, and for which values of X I would be assigning it to the class 2. No, tell me what is the region of, see, this is your X bar, your x-axis is X bar. I give you an X bar value, okay, at least for these graphs. How would you say whether that belongs to this one or that one? Okay, assume that they have equal variances and just the mean is varying. Okay, the implication of what I mentioned would become clear to you later points of time, but at least by looking at these graphs, you tell me. When do you assign a given pixel to omega 1, given an X bar to omega 1, and when do you assign it to omega 2? And the condition is given here, that's already is there here. This is the condition. Now how do
So
you
like in
interpret it in terms of this graph is all I'm asking.
So if
Where
it
do
is
you
point
put a
of
line?
intersection,
Very
consider
good,
the point
very
of
good.
intersection. If it is less than, we
Correct,
assign
correct.
probability
Excellent.
of X by
Very good,
omega.
very good. This I would call it as R1. This I call the rest as R2 here. Notice here, beyond this point of intersection, which probability is more? The probability
Omega 2.
before this point, it is the probability of omega 1 is more here. Beyond this point, the probability of X bar given W2, the likelihood of the second class is more after this point compared to the other one. You could see here, if I assign it to this class, for example, an X bar here, okay, that's fine, it has more probability. But if I assign to this class, that likelihood is only this much, that probability. Whereas if I assign it to this, that probability is more. So it is the intersection point here that tells me that till that intersection point, I would assign to this, and beyond that, R2, I'm calling it here, that I would assign to the other class. I'll stop here in the interest of time.